In part 2 of section 8, we're going to be looking into a concept called types of linear systems. And what's going to be the driving force behind this is the idea of how many solutions could there possibly be for a linear system of equations. And there are three ways that we can classify a linear system. We can do it geometrically, we can do this by its independence, and we can do this by its consistency. Let's start with the geometric approach, and let's think about how we could take two lines and have them be situated in the same Cartesian coordinate plane. And it helps to think about having maybe two pencils laying on your desk, and you want to try to arrange them in different ways on the same plane. Would there be a pattern to this? Would there be a way that you could somehow fit all the different ones into different categories? And there, in fact, there are three categories that we can take every linear system, and put it into one of the three categories. It would be, the first one is called intersecting. The second is called parallel. And the third is called same. So for intersecting, that would be any two lines that end up intersecting at one point in the Cartesian coordinate plane. When this occurs, and this is what happens a lot, you will get two lines that are in a system, and then they will end up crossing each other at some particular point. That means that there is only one solution to this system. So any point that is on a line is a solution of that line, but there's only one point that would be considered an ordered pair for both of the lines, and that would be the place where they are intersecting. So that would be where the one solution exists for this particular type of system. In a parallel line situation, you would have two lines that never touch each other. We talked about parallel lines in section 6 when we talked about linear functions, and we know that parallel lines have the same slope, and then they have different y-intercepts. So if that's the case, they never touch each other. So any of the ordered pair that are on this line would not also be a part of this line. So if they don't ever have any ordered pair in common, then there are no ordered pair that would make each equation true. So this would be an example of when we would end up having no solution, or we would call that our empty set for the solution set. And then the third possibility is the same line. So if you have a line, let me use red to illustrate the second line so you can see that there is another one right on top of it. You have two lines, one on top of the other. So in that situation, every ordered pair that's on the blue line would also exist on the red line. So therefore, there would be infinitely many solutions. A lot of solutions. But there would also be a lot of ordered pair that are not solutions to this. So when we say infinitely many, it doesn't mean every conceivable ordered pair, because there's an ordered pair right here that's not a part of either one of those lines, and that ordered pair does not get to be a part of the solution. So we're going to have to talk more later on about how to actually document which infinitely many solutions we want, which ordered pair do we want, and which ones do we want to leave out, because there's just as many that we want as that we don't want. So we'll talk more about that later on. And that's the geometric approach to classifying your linear systems. You either have an intersecting lines case, a parallel lines case, or a same lines case. Now, the next thing I want to do is classify these by independence. So with independence, you have one of two vocabulary words to work with, either the word independent or you have the word dependent. Now, the idea of independent versus dependent has to do with the question, are the equations different? If your equations are different in the system, then that means that the system is independent. If your equations are actually the same, then that means that your system is dependent. So for example, if I was to look at the intersecting lines case, the intersecting lines has to have two different lines in order for them to only cross at one point. If I have two different lines, that means that each one of them would have a different equation. So intersecting lines is an example of an independent system. One of the other two is also considered independent. That would be the parallel lines case. In parallel lines, you have two lines that are different from each other, therefore their equations must be different from each other. I know that they have the same slope. Parallel lines must have the same slope, but because they would have different y-intercepts, that would officially make their equations different. So this is also an example of an independent system. And then finally, the same lines case. Well, if you have two of the same line, then it doesn't matter how you write it, you have the same equation. So that means that this is a dependent system. So that's what we call classification of independence. Then we have classification by consistency. So for consistency, your system is either consistent or it is inconsistent. Those are the only two options we have there. Now for consistent versus inconsistent, we're going to be asking ourselves the question, does a solution exist? If your system has a solution, that could be one, that could be 2, 3, 4, infinitely many, whatever. If it has a solution, at least one, it's considered a consistent system. If it doesn't have any solution whatsoever, then it's considered an inconsistent system. Now there's only one system up here that doesn't have any solution at all, and that's the parallel lines case. So the parallel lines is going to be our only inconsistent system. Intersecting lines, of course, has exactly one solution, and all we have to have is at least one solution in order for it to be considered consistent. And then the same lines case, we have, well, infinitely many solutions, so that's definitely at least one. So this is also an example of a consistent system. So there's three ways to classify a system. Now, probably most often we'll be doing the classification by geometry, but it doesn't hurt to also know these other vocabulary because it'll help you to be able to identify the relationship between the equations and the solution.